Okay, welcome back to your calculus adventure. This brings us to a new chapter. By the way, here's how you should think about chapters 2 and 3. The second chapter of this course is really a study of limits, specifically to pave the way for developing the derivative, which was in the last section, right, 2.5. The purpose of chapter 2 is really to show you what is under the hood of the derivative, how it works, what it is, and what it gives you. But often we don't need to think about all those details when we're working with the derivative as a tool, and that's where chapter 3 is going to come in. We're going to develop some more efficient methods of calculating derivatives that are more useful when you're using the derivative in practice. But this shouldn't be misunderstood to downplay the importance of the limit definition of the derivative, because in fact that's exactly where these rules are going to come from, as we'll see when we derive them. Okay, so the first rule we'll talk about is, well, what do you do when you get a constant function? Okay, so here's how we'll start. The derivative of any constant function, f of x is equal to c. So here's a definition of a general constant function. We've kind of already made it clear that c is a constant by mentioning constant function here, but just to be absolutely clear, we'll say where c is a constant real number. So where c in the reals is constant. Now there's no doubt. Okay, so what is the derivative of this sort of function given by? Well, we can compute it from scratch just using the limit definition and see what we get. Okay, so, well, if we're going to compute f prime of x, well, by definition, that's the limit as h goes to 0 of f of x plus h minus f of x all divided by h, right? That's just applying the limit definition of the derivative to the function f. This is not even taking into account what the function actually does, but that's what we're going to do on this step. So what is f of x plus h? Well, f of anything is the constant c. That's how constant functions work. No matter what you plug into f, you're going to get c back. So f of x plus h, this is going to be c. So we haven't taken the limit yet. We're still going to write that in front. Limit as h goes to 0 of c minus, and then f of x, that's also going to be c. Right? So we have c minus c divided by h on the numerator. Okay, and, well, what do you notice? You notice right away you can clean up the top, right? You can go c minus c is equal to 0, right? The numerator of this fraction is 0. So you get the limit as h goes to 0 of 0 over h. I'm being very careful here to do everything one step at a time. And then now, 0 divided by h is just 0, right? 0 divided by anything is 0. Because remember, as far as this limit is concerned, h is a number that's getting close to 0, but it's never actually equal to 0. You're never actually going to plug in 0. So this fraction is well defined, and it's got a numerator of 0, and the denominator is non-zero, so therefore that fraction is always equal to 0. So you get the limit as h goes to 0 of 0. Really, what you have here is the limit of a constant. That constant is 0. You get the limit as h goes to 0 of the constant function 0. Well, one of the first properties of limits we saw in section 2.3 was that the limit of a constant is always just that constant. So in this case, that limit is going to evaluate to 0. It doesn't matter what h is doing. If your function is constant, the limit is going to be equal to that constant as well. So what this tells you is that f prime of x is equal to 0. So therefore, the derivative of any constant function is equal to 0. So let's summarize that in a rule so we don't have to do this calculation again in the future. So therefore, and for stating these rules, I like to use operator notation. So here's the way I'll say it. The derivative with respect to x of any constant function, c, is equal to 0. And let's elaborate to make this really clear where c in the reals is any constant. Okay, so that's our rule. Okay, so you never have to take the derivative of a constant function using the definition again. You can just use this much quicker rule. If you have a constant and you're taking its derivative, you're going to get 0. Really, that makes sense if you think about what the derivative gives you, right? It gives you the slope of a tangent lines. It gives you the slope of tangent lines. And constant functions, graphs, are flat lines. So any tangent line should be flat as well, and therefore it would have a slope of 0. So geometrically, that's the reason. But analytically, this is how you can calculate it. Okay, that's the first rule. Let's look at another rule. For any constant c, again, for any constant real number c, and any function f of x, define g of x is equal to c times f of x. So you can see we're defining this, we've got some function f of x fixed in the background and some constant c. And the idea is we can define a new function g by just setting g of x to be that constant times f of x. And really the point of this is what we're going to do is look at how the derivative of this new function g compares to the derivative of the underlying function f. So that's the purpose of this. So let's see what happens. Let's compute g prime. So g prime of x, we'll start with the definition. Right? Start with the limit definition. If you don't have a rule for this type of function, then you just start with the limit definition. That's going to be always what you do. So by definition, this is g, the limit as h goes to 0 of g of x plus h minus g of x all over h. Okay, and then now we're going to actually apply what g does. Right? What does g do to an input value x? Well, it plugs that input value into f and then multiplies the result by c. So we're going to get the limit as h goes to 0 of c times f of x plus h. That's the g of x plus h. And then the g of x is just going to be c times f of x. So minus c times f of x. I have an extra pair of brackets there. It's not really necessary, but I don't need to bother erasing them now, right? C times f of x. I didn't really need these brackets, but I just did them by accident. Anyways, that's fine. So we've got two terms in our numerator now, c times f of x plus h and c times f of x. Well, both of those terms have a common factor of c, so we can factor it out. And I think I'll do one more step here. Limit as h goes to 0 of c times f of x plus h minus f of x all over h. Okay, so that's what you get if you factor out the c. Okay, I'm going to take one more step just to pull this c out of the fraction. Right, so you'll see what I mean after I write this step down. I can think of that c as multiplying onto the numerator like it currently is, or I can pull it right out of the fraction and interpret it as c multiplied by the fraction f of x plus h minus f of x over all divided by h, like this. So c times f of x plus h minus f of x all over h. Okay, so that's what I can do. And now another property is of limits is that constant multiples can be pulled out of limits. That was one of the properties we saw of limits in section 2.3. So we're going to take advantage of that now. And I want to actually highlight this just to make it clear what's happening. This c is being pulled out of the limit. So that's what our next step is. We're going to have c times the limit as h goes to 0 of f of x plus h minus f of x all divided by h. And really, so up to this point, all we did was take advantage of limit properties and algebra. Every step so far has been just either an algebraic step, like the first few, or taking advantage of limit properties. But now, what you see is what's this equal to? Everything inside this green bubble is really just f prime of x, right? This is equal to f prime of x. So what you get now is c times f prime of x. So summarize, what does that mean? That means if we wanted to take the derivative of g of x, we can really just take the derivative of f of x and multiply the c on after. That's really what this is, right? This is take the derivative of f of x, that's what f prime of x means, and then the c gets multiplied on after. So that tells you how you can deal with constant multiples inside of derivatives. Really, it turns out that it's really much the same as the way you can deal with them when you're dealing with limits. You can pull them out. So if I state the rule in operator notation, it's going to look like this. Therefore, the derivative with respect to x of a constant times some function of x is just going to be equal to that constant times the derivative of f of x. That is our rule in operator notation. So let's put a box around that because that's also going to be quite important. Okay, so that tells you a really nice fact that constant multiples can be pulled out of derivatives. Just like this constant multiple got pulled out of the limit, this rule is saying you can essentially do the same thing with derivatives. So that's a nice property, especially when you combine it with the rule we're about to talk about right now. Okay, so we'll start a new rule now. So let f and g be differentiable functions. All right, well, what are some things you can do if you have two functions? What can you do with them? Oh, by the way, differentiable functions, what that means is just that you can take their derivatives. Let's assume in advance that we've got two functions f and g that have some derivatives that you can calculate. Because remember, the definition is based on a limit, so sometimes that limit won't exist. So let's just assume we have two functions f and g that you can take their derivatives. That's what I mean when I say let them be differentiable functions. Well, what are some things you can do with functions if you have two functions? Well, one of the simplest things you can do is add them together. So let's define capital F of x to be little f of x plus little g of x. And then we'll compute the derivative of capital F. So in other words, we're going to see what is the derivative of the function that you get if you add these two functions f and g together. Right? And the idea is we're going to see if there's any relationship between the derivative of capital F and the derivatives of little f and little g. So let's start by just calculating the derivative of capital F. And just like in the previous two rules, we're going to start by using the definition. Okay, so let's write down the limit as h goes to 0 of capital F of x plus h minus capital F of x all over h, right? All right, well, let's now apply what capital F does. What does capital F do to an input value? Well, it takes that input value and it plugs it into little f and little g, and then it adds the results together. So let's apply that here, where you get the limit as h goes to 0 of little f of x plus h plus g of x plus h. So that is your capital F of x plus h. And then we're going to subtract capital F of x, which is really just going to be f of x plus g of x. And then all of this, of course, is divided by h because we haven't touched the denominator. All right, well, let's do the next step over here. So let's distribute this subtraction into the brackets and maybe reorganize the terms on the numerator a bit. We can write this in the following form. The idea is let's group all the f terms together and group all the g terms together. So I'll get the limit as h goes to 0 still because we haven't touched that yet. And on the numerator, I'm just going to write f of x plus h minus f of x. So I'm really talking about this term, which is positive, and this term, which is negative. And then for the second two terms, I now have g of x plus h, which is positive, and then g of x, which has a negative in front of it. So I'll have plus g of x plus h minus g of x, and that's all divided by h. All right. Now we're going to split this fraction up using properties of fractions. So let's write this as the limit as h goes to 0 of f of x plus h minus f of x all over h plus g of x plus h minus g of x all over h. All right, and now we're almost done because now we have the limit of two functions of h, right? For every fixed value of x, think of x as a fixed value. For every fixed value of x, this is a function of h, and this is a function of h. We're adding them together and taking the limit as h goes to 0. Well, one of the properties of limits says if I have the limit of a sum of two functions, I can split that up into the sum of two separate limits, which is exactly what we're going to do now. So we have the limit as h goes to 0 of f of x plus h minus f of x all over h plus the limit as h goes to 0 of g of x plus h minus g of x all over h. And now you might recognize something, because limit as h goes to 0 of f of x plus h minus f of x all over h. If you just look at this part here, this looks familiar, right? This is exactly the derivative of little f. And this limit here, limit as h goes to 0 of g of x plus h minus g of x all divided by h, this is exactly the limit definition of the derivative of little g of x. And we're adding those two things together. So what we're going to get, finally, for our result is f prime of x plus g prime of x. Right? So it turns out if you have capital F and you define that to be the sum of the two little functions, or two functions little f and little g, then the derivative of capital F is just going to be little f, the derivative of little f plus the derivative of little g. So in other words, the derivative of a sum of two functions is equal to the sum of each of the derivatives of the respective two summands. So let's write that in operator notation. There's room up here to say it, so I'll say the derivative with respect to x of the sum of two functions, f of x plus g of x, that's equal to the derivative of f of x plus the derivative with respect to x of g of x. So it just says you can split up derivatives if there's a sum involved. So if there's two functions being added together and then you're taking the derivative of the result, turns out you can take the derivative of the two pieces separately and then add them after. That's the main purpose of this rule. And it turns out there's a similar rule for subtraction, which we won't prove that one in detail. This one, the proof is in the work we did here, but there's a similar rule for subtraction, which I'll write down on the next page, but we won't prove that one. I'll leave that to you as an exercise to prove it on your own for practice. And you can see that it works out in the exact same way pretty much.